So welcome folks to the climate seminar series. This is the last in the series that we've had for 2021 and one I've been looking forward to for a while. We have Dr. Amy Butler from the NOAA Chemical Sciences Lab out in Boulder. Her job out there is to study large-scale climate variability, teleconnections, atmospheric dynamics, stratospheric processes, and sub-seasonal to seasonal prediction. Her interests particularly lie with the stratospheric polar vortex and its influence on surface weather and extremes. So her background and interests really tie with what can affect us in climate timescales. She got her PhD from Colorado State University and has actually worked at the Climate Prediction Center before moving out to the lab in Boulder. A couple of logistical things before we start. This webinar is being recorded, so folks will be able to review it or attend it later on. And if we can hold questions to the end, we'll have a question and answer session that Jenna will moderate, so you can put your questions in chat and we'll answer them at the end of the presentation. And without further ado, Amy, the floor is yours.
Great, thank you so much. And thank you for inviting me to speak today on wintertime impacts of polar stratospheric variability. As Ray mentioned, I previously worked at the Climate Prediction Center, and now I'm at NOAA CSL, where I've been for the last 8 years. But my research still focuses a lot on subseasonal to seasonal prediction. And today I'm going to be giving some hopefully useful background about how winds in the stratosphere can influence surface weather, and particularly over North America. So let's see if I can get this thing to go forward. There we go. The stratosphere is the layer of the atmosphere 10 to 30 miles above the surface, and it's just above the troposphere, which is the region where we have all our weather. And an important feature of the stratosphere is that it's the home of the ozone layer. And this obviously is very important because it acts as our natural sunscreen to dangerous UV radiation. But it's also because of the ozone layer that the stratosphere acts a bit differently than the troposphere. For example, unlike in the troposphere where the temperature tends to decrease with altitude, in the stratosphere the temperature actually increases with altitude because the ozone warms this layer as it absorbs radiation. So the feature of the stratosphere that I'm going to be talking about today is the stratospheric polar vortex. And the term stratospheric polar vortex simply describes the westerly circumpolar winds in the winter hemisphere stratosphere. And so there's a polar vortex in both the northern hemisphere and in the southern hemisphere during winter. And I'm just going to be focusing on the northern hemisphere polar vortex today, but in the southern hemisphere there are also surface impacts from the polar vortex. So this image is from earth.nullschool.net, and it's just a snapshot in time of the polar vortex winds at 10 hectopascals, which is about 30 kilometers above the surface. And it was taken on February 16th, 2020. And if you go to this website, it's a great web page where you can look at the winds moving around the globe in different places. And this was a particularly striking image to me because the winds were actually exceptionally strong in the polar vortex on this day. The winds here, there's no color bar or anything, but where you see the purple lines, that's about 120 miles per hour. So typically the winds in February at this level are about 45 miles per hour. So it was exceptionally strong. You'll also notice that it's very circular. It's very centered on the pole. Normally the Northern Hemisphere polar vortex is a lot wavier. And so this was kind of an unusual event, but this feature of winds as they move from west to east around the pole is not unusual, but actually just a regular feature of every winter. So why do these winds occur? Well, these winds are due to the seasonal changes in incoming amounts of sunlight. So as the Earth begins to tilt away from the sun during fall, the sunlight or the lack of sunlight over the pole starts to cool the stratosphere, and this drives an enhanced temperature gradient from equator to pole. And due to thermal wind balance, that means you get enhanced westerlies with height into the stratosphere. So to measure the stratospheric polar vortex, the typical diagnostic that we use is the zonal mean zonal winds at 60 degrees north and 10 hectopascals. And so this plot is using reanalysis data, and it's just showing the daily mean winds at this level and latitude over the entire 1958 to present day record. And it's taking an average. So the black line here is this daily mean average over the entire record as a function of day of year. And so what we can see is that in July and August and June, the winds in the stratosphere are easterly or negative. But towards the end of August, the winds turn westerly, and this is the formation of the stratospheric polar vortex, which then amplifies into late December before it starts to weaken again as the sunlight returns to the pole. You'll notice that there's also a lot of variability in the stratospheric polar vortex in wintertime, and that's denoted by the gray shading. So the top gray shading line is the daily maximum winds in the historical record, and the bottom line is the daily minimum values. And so we can see that there are extremes in this time series that occur either when the polar vortex is extremely strong, where sometimes you can see winds exceeding 60 meters per second, and the other extreme is when the vortex winds actually, though they're typically westerly or positive, they can actually change sign and reverse and go easterly, so they change direction. And this is called a sudden stratospheric warming. So I'm going to be talking about that a little bit more in the next few slides. So why would we care about these winds that are, 30 kilometers above us? Well, the important thing about it is that the troposphere and the stratosphere interact with each other. And this is a two-way coupling, so that the troposphere can influence the stratosphere, and then the stratosphere can then influence the troposphere. And so in terms of the upward coupling, the troposphere affecting the stratosphere, what we found is that there are things like weather systems, such as blocking patterns and land-sea contrast, that are associated with these large-scale, planetary-scale atmospheric waves. And these can amplify into the stratosphere as long as the background flow is westerly. And so this is really the important thing about the polar vortex, is that when it forms, it suddenly basically opens up the channel for the troposphere to have an influence onto the stratosphere. And so once we are allowed to have that communication between these two levels, the vertically propagating waves can dissipate or break in the stratosphere. So you can imagine this sort of like an ocean wave breaking on the beach. So when that happens, when the ocean wave breaks on the beach, it deposits a lot of heat and friction at the sand on the surface. Well, in this case, it's similar. There's these big waves in the atmosphere. They're going up and they're breaking against the polar vortex, essentially, and they're depositing easterly momentum, and then they slow the westerly polar vortex. And this happens very rapidly. That's not the only process that can disrupt the vortex. The other is that the vortex, the stratosphere itself, can sort of self-tune itself into something that has some internal resonance and can sort of pull itself apart. And so these two processes, this combination of internal resonance and the momentum deposition from planetary scale atmospheric waves that break, can drive what's called this major sudden stratospheric warming event. And so this is defined as when the zonal mean zonal wind at 10 hectopascals and 60 degrees north reverses direction. And so this plot up here shows some configurations of what typically happens in the stratosphere. And so this is showing the black lines give you the potential vorticity at in the lower stratosphere at 550 K. And it's basically just telling you the shape of the polar vortex. And then the shading is showing us the temperature anomalies at 10 hectopascals. And so what we see is that one configuration is just a strong polar vortex that's similar to the plot I showed before from the earth.nullschool.net, where it's very circular and the temperatures within the vortex are much colder than normal. And then when we have a sudden warming, what happens is typically either the vortex can be sort of knocked off the poles, which is the case of a vortex displacement. So you can see here, it's kind of been knocked over towards Eurasia, or you can have a split of the vortex. So the polar vortex can actually be ripped apart into two smaller vortices. And you see in both cases, you get a very strong warming of the stratosphere. Typically, this is about 30 to 40 Kelvin in just a matter of days. So it's a substantial change in the circulation. I wanted to share a little image of this to get a better idea of what's actually going on. And so what this is showing us is the sudden stratospheric warming that happened in January 2009. And at the very bottom, you can see sort of a time series, and the star is telling you what day the image is on. And so you can see that the winds are westerly at that 10 hectopascal 60 north level, and then they reverse direction on January 24th, 2009. And what's happening in the stratosphere when that's going on, and this is all levels that we're looking at in the stratosphere, none of this is surface level. And so the shading here is the temperature in the stratosphere at 10 hectopascals, and those black contours are again showing the shape of the vortex. So at the beginning, you can see it starts off very circular, then it starts to elongate, and then right around here, it starts to rip into two pieces, and then the two pieces go in different directions. And you'll also notice that the arrows here are showing the wind direction, and they're black when the zonal mean component is westerly, and then they're blue when the zonal mean component is easterly. So you can see that by the end of this, what's essentially happened is that this huge circulation in the stratosphere, it's basically hemispheric wide, has completely, changed around its entire course. So to me, this is like a really cool event. And I think a lot of dynamicists, this is sort of like the key phenomenon in the atmosphere. This just makes you really excited about dynamics because it's so impressive. But if it was just for this happening in the stratosphere, we probably wouldn't care that much about it because it's a cool thing, but if it doesn't have an influence on our lives, we wouldn't study it so much. So really the essential part of these events is that they have an important downward influence. And so what this plot shows on the left here is the Northern Annular Mode Index, which is just an index that describes the pressure variations between the polar cap and the mid-latitudes. And so a negative northern annular mode, which is what we get when there's a sudden stratospheric warming, would mean higher polar cap heights and then lower heights over the mid-latitudes. And so that's just what this is showing, and this is just an average over all the sudden warming events that have happened in the historical record for the 60 days before the event happens and the 60 days after. And so you can see this huge change in the Northern Annular Mode Index, obviously in the stratosphere when it happens, but this signal actually propagates downward to some extent, but it also just persists in the lower stratosphere for a long period of time. You can see in the mid-stratosphere, the vortex is recovering quite quickly within a matter of a couple weeks. But in the lower stratosphere, we get longer radiative timescales. And so once you change the circulation at that level, it tends to just hang around. And so this is really the key thing about the polar vortex, is that if it can change those lower stratospheric anomalies, that gives us some memory in the system that we can use to improve predictive skill. The important thing to note is that the downward influence, this is an average on the left here of all the sudden warming events, so it averages out a lot of the noise. But the downward influence can vary significantly on a case-to-case basis if we're just looking at individual events. So that's what's shown on the right side. It's the same metric, the NAM index, but it's for two separate sudden warming events. One is the February 2018 event, and one is the January 2019 sudden stratospheric warming. And the black dotted line is where the sudden warming occurred. So you can see there are substantial changes in the stratospheric NAM, but you can see that they had very different influence below on the troposphere. And so here you can see in 2018, there was an almost immediate influence downward, whereas in 2019, there was really very little influence until maybe several weeks or even a month later. And this is important because when we're trying to use these events for things like week 3-4 prediction, where this is, I've marked week 3-4 in purple lines here on this graph, you can see that that would mean really different things depending on which event we were looking at. So if you were a forecaster and trying to use this event to make a prediction at the surface, it can be very difficult because these events have a lot of variability going on in the troposphere. And I'll bring this up at the end a little bit too. But in terms of the average influence of these events on the surface, there's some key things that we notice. And so this upper plot here on the left shows the average surface temperature, precipitation, and mean sea level pressure changes for the average days 0 through 60 after all historical sudden warmings. And so what we see is higher than normal sea level pressures over the Arctic cap, and then lower than normal pressures over the mid-latitudes, but particularly over the North Atlantic. So this is congruent with a negative North Atlantic oscillation. And the negative NAO is known to have substantial influence on surface temperature anomalies and precipitation. And we can see that in these averages here. After the sudden warmings, we get increased cold air outbreaks over most of the mid-latitudes, in particularly over Eurasia and over the eastern US, and anomalously warm temperatures over Greenland and subtropical Asia. There's also precipitation anomalies associated with this, including much wetter conditions over southern Europe and much drier conditions over Scandinavia. And you'll see that there isn't much change in precipitation that's significant over the US. So these are sort of the canonical things that we think about when we're thinking about a sudden stratospheric warming. It's important to note that I've here focused on one side of the extremes of the polar vortex, which is when you have a really weak polar vortex and what that does to the surface. But like I showed in that time series plot, there's also times when the polar vortex is very, very strong. And this is also associated with downward influence on the troposphere. When we have a stronger polar vortex, we essentially get the opposite conditions that are shown in this map here with positive NAO, which means a warmer winter over the eastern US, Europe, and Asia, and drier over southern Europe. And these also are persistent and potentially predictable. So this little schematic in the right here is from NOAA, and some of the NOAA Stratosphere people helped put a new image like this together this year. And it just kind of summarizes these two concepts, which is that you can have a very stable and strong polar vortex, in which case the polar jet stream stays farther north and the cold air over the Arctic is contained over the Arctic. So it doesn't go into the mid-latitudes. Or you can have a disrupted polar vortex where it has some influence on the jet stream below it. It causes it to be slightly wavier. And so you get this cold air outbreaks moving in from the Arctic and even warmer air moving north in some regions. So it makes it a little bit more variable is the idea. So I want to have a quick aside on the term polar vortex, because I know that there's always headlines like this that suggests, you know, the polar vortex is on its way, or the polar vortex is about to strike Britain. And this has been done fairly often since about 2014. It's used almost as a synonym for cold air outbreak. However, scientists have been using the word polar vortex for many decades to refer to the climatological westerly wintertime winds in the stratosphere, just this regular feature in the stratosphere that always occurs. And so the polar vortex can't really like come and get you or go to a certain area and deliver weather. It's just up there all the time in the wintertime. And actually, it's usually the disappearance or the disruption of the polar vortex that makes these cold air outbreaks more likely. When you have a strong polar vortex, you're actually getting warmer weather in the mid-latitudes. So the last point I wanted to make is that, you know, the polar vortex is up in the stratosphere and it can sometimes load the dice for you to get these cold air outbreaks. But, you know, the jet stream's doing its own thing most of the time. And so you can get colder outbreaks independently of changes in the polar vortex. The polar vortex just gives you some predictability that, or increases those chances that these colder outbreaks might occur. Okay, the other thing I wanted to discuss is that so far I've talked mostly about sort of this, if we look at these sort of plots, this is a really zonal mean sense of what's going on. In other words, I'm averaging here over basically all the longitudes to get a plot like this. And so we're getting a sense for what's going on right over the polar cap, but not really understanding the asymmetries that come along with one of these events. And of course, when you have a sudden stratospheric warming, it's highly non-zonal. And so we can see that clearly in this little video that NASA made. This is for the February 2018 sudden stratospheric warming. And so here the shading is showing the potential vorticity in the stratosphere. So it's just showing you the shape of the vortex again. And so you can see how really fluid-like it is when this happens. And as those pieces sort of shear off from one another, you can see how asymmetric this is in the stratosphere. The thing I really like about this video, though, is that it also has these red contours, which are a little hard to see, but mark the 200 hectopascal heights. So it's basically showing you where you're having ridging and troughing in the troposphere. And you can see when this little blob breaks off over towards the Canadian sector here, that the jet stream is sort of being pushed south in a way. It's being nudged south. So the idea here is that these zonal changes, these azonal changes, can have a big influence on where the weather impacts will be felt. And this has been only really recently discussed very much in the literature, but this paper by Marlene Kretschmer in 2018 is really nice, and it shows, it basically looks at patterns in the stratosphere and what sort of temperature responses they correspond with. And so she highlights two of these patterns. One is this cluster 5, which basically is just a higher than normal heights over the entire polar cap and represents sort of our canonical sudden warming image where the vortex weakens a lot and the heights are high. And associated with that, she shows that the temperature anomalies look very much like this sudden warming composite that I showed earlier, with cold temperatures over Eurasia and warm temperatures over Greenland. But it's this other pattern, cluster 4, which is really when the vortex is more off-center and nudged towards Canada, and you get kind of a stretched out polar vortex, and that's where we see the most cold over North America. So it's not during these really strong sudden stratospheric warming events, but rather it's a different type of structure that causes these cold anomalies. And this was further highlighted in a recent study by Simon Lee et al., where they looked at wintertime North American weather regimes. And so what they did is they first calculate the weather regimes in the troposphere, and I'm not showing those patterns here, but then they say, what is the stratosphere doing during that time? And so that's what's shown on the left here. And similarly to the Kretschmer study, they find that sudden warmings are associated with an Arctic high pattern in the troposphere, where you get this generally weak pattern of a vortex over the polar cap. And these is again associated with much colder temperatures over places like Europe. But where they see the coldest temperatures over the US is actually during this Alaskan ridge phase. So when you have a strong ridge in the troposphere over the Aleutian Islands, you basically get this really stretched polar vortex with anomalously low heights over the Canadian region. And this is where we're seeing the coldest temperatures over North America. So the primary influence of the polar vortex on North American weather may not be from sudden stratospheric warmings. And I think that's just starting to be appreciated, and it could be very important for improving weather prediction here in the US. Before I move on, I just wanted to again highlight that a strong polar vortex can also drive surface extremes, because the focus tends to be a lot on these sudden stratospheric warmings, but when the polar vortex is very strong, we've seen significant surface influence. And an example of this happened in 2020, and this is from a paper by Zach Lawrence in 2020, and it basically just shows how anomalously strong the winds in the stratosphere were between about 60 and 80 degrees latitude at 10 hectopascals. And they really persisted throughout the stratosphere and then down to the surface all the way from December 2019 well into April of 2020. And if we look at the observed wintertime surface temperature anomalies during that time period, you can see very strong anomalous warmth across most of the mid-latitudes. In fact, it was the record hottest winter in many locations, particularly over Russia and Asia. And we found in this study that about 2/3 of that warmth could be explained by the extremely positive Arctic Oscillation or Northern Annular Mode Index, which was associated with this strong two-way coupling between the stratospheric polar vortex and the surface. The AO was actually the highest in the 70-year record. And so there's definitely an influence on the other side of these polar vortex extremes too. So we have done some analysis of the role of the stratosphere in subseasonal to seasonal prediction models using models from the S2S prediction project. And in this study by Daniela Domaison in 2020, we looked at all the models that were part of this. That includes the NOAA CFS model. And we divided the models into what we call high top models, which have a model top above 0.1 hectopascal and several model levels above 1 hectopascal, and the low top models, which didn't meet those criteria. The reason we do this is because we found with coupled models that those models with the high top generally have better stratospheric variability. So they capture things like sudden stratospheric warmings better. So what we found in this study is that in general, as you might expect from earlier results that I've shown, the stratosphere has longer memory than the troposphere. And so this is just showing anomaly correlation maps for 50 hectopascal heights on the top row and 500 hectopascal heights on the bottom row. And it's just looking at when the skill in that in those heights basically goes below 0.6. So 0.6 was sort of our skillful level of prediction. And it does this for the annual mean in the left column and wintertime in the middle column and summertime on the right column. And then just to kind of summarize, at the bottom here, I've included the day at which that skill level falls below 0.6. And so you can see on average in the troposphere, no real surprise here, but it's about a week for predictability at 500 millibars. But you'll see at 50 millibars, it's actually about double that in the annual mean. And even slightly, you know, we get 16 days of skillful prediction at 50 millibars in the wintertime. This goes down in the summertime because the vortex is gone, then it's just easterly winds. But surprisingly, also even in the summer, the stratosphere is more predictable than the troposphere. We also found that models with longer prediction skill in the stratosphere also have longer prediction skill in the troposphere. So this is then just taking that day at which the skill falls below 0.6 at 500 millibars on the y-axis and 50 millibars on the x-axis and comparing those two. And what we found is that for each point as an individual model here, these are well correlated. So at 0.96 in wintertime and 0.89 in summertime. So we're seeing that you know, if a model has a good stratosphere, it generally tends to also have higher skill in the troposphere. However, the direction of causality here can't be inferred because obviously a model that's really good either in the troposphere or stratosphere might just be a better model. And so we wanted to know, well, if we look at, what about if we look at forecasts of opportunity, if we look at forecasts that are initialized when the polar vortex is weak or strong compared to control forecasts where the stratosphere is not doing anything. And so what we did is we basically classified what the stratosphere was doing at 10 millibars and 60 north at the time of initialization for all hindcasts from December through March. And if the winds were below 5 meters per second, it was considered a weak vortex. And if the winds were stronger than 40 meters per second, it was considered a strong vortex. And first we looked to see, well, what is the temperature response 3 to 4 weeks after this happens in the model? And so we just kind of composite those all together. On the left, we're looking at the error interim composite. So again, you can see during weak vortex events, we get that sudden warming looking type map with cold air over northern Eurasia and the US. And in general, the models are capturing this pretty well in terms of the average, what the pattern should look like. So they are capturing the stratosphere-troposphere coupling as we would expect it to. And it's doing the same thing for strong vortex events. Again, you're getting basically an opposite signed response as you do for the weak vortex events. But then we wanted to look at the surface skill, the predictive skill. And here we're using a very simple metric for skill. So perhaps these results would be different if we used slightly something more sophisticated. But this is just the anomaly correlation. And what we do is we compare the forecast during these weak vortex events with control forecasts, which are basically subsampled forecasts where we use the same date of year, but for randomized years in the hindcast record that don't have anything going on in the stratosphere. And so here shows the control skill. On average, you know, it's fairly minimal because we're looking at week 3, 4. So it falls between 0.2 to 0.3 correlation values. And this is after the weak vortex events. And so if we subtract these, you can see where the skill improves or doesn't improve after these weak events. And surprisingly, well, we do see skill improvement over a lot of Asia and even the central US and parts of subtropical Asia. The skill actually decreases over Europe, which is where we actually typically see the strongest impacts from these events. So this was pretty surprising to us. And it might have to do with the fact that, again, because what happens to the jet stream after these events is highly variable and it depends a lot on the timing. You know, the model could be predicting just an overall, you know, oh, it's going to do this exact thing, but it might not do that at the exact week 3, 4 that we're looking at here. And so there could be some disconnect between what the model's predicting it should do and what actually happens when there's a lot of other variability. The other important point is that the accurate detection of sun warmings themselves generally can only occur at 10 days or less. And that's what this plot is showing. So we looked at all the different S2S forecast models, and we looked at when the majority of their ensemble members were able to capture either a strong vortex event or a sudden stratospheric warming event as a function of lead time. So you can see that when they exceed about half of their members, on average occurs only in the 10 to 6 day lead time or less time frame. And in some ways this makes sense because these events are largely driven by unpredictable tropospheric waves that are associated with weather patterns. And so they're not going to have a longer predictability than weather itself. We did find that models with the higher model top and vertical resolution did detect these events at slightly longer lead times. So the question, of course, arises, can we make probabilistic forecasts of sudden warmings for seasonal forecasts, given the inherent limitations of deterministically forecasting sudden warmings? And so there are a number of factors that can increase the probability of sudden warming events over a season. And I've just sort of listed them here. There's actually quite a lot. So we found that there's a 30% higher frequency of sudden stratospheric warmings in El Nino in particular, relative to a neutral ENSO. The Madden-Juliet oscillation has been found to show a higher chance of sudden stratospheric warmings 1 to 3 weeks following phase 6-7. And then the quasi-biennial oscillation, which is this tropical oscillation of winds in the lower stratosphere, shows more sudden warmings in the easterly phase, but this may be modulated by the solar cycle. And then there's a number of other factors that people have pointed to, things like Eurasian snow cover, North Pacific sea surface temperatures, volcanoes, and Arctic sea ice. All these things people have investigated as ways to improve the predictability of these sudden warming events. So this is good, but in practice, this tends to be very messy. And this plot kind of demonstrates why this is tricky. And it's basically just showing two of these factors. One is the November through January QBO, shown on the y-axis, and then the November through January Nino 3.4 index, which is shown on the x-axis. And what it's showing is just a point for what the index values for these two things were in any given November through January period. But the little dots that are shaded in a color, either red or blue, are winters that had a sudden stratospheric warming. The open circles with nothing in them are winters where there was no sudden stratospheric warming. And so what we see is that, first of all, sudden warmings have occurred in pretty much any phase of QBO and ENSO. However, if we then start to look at the statistics, and those are kind of shown here in each little quadrant for different phases of the QBO and ENSO combinations, there are variations in the frequency of sudden warmings depending on what you're looking at. So, for example, we see the highest frequency down in the lower left quadrant, which is an easterly QBO and a La Nina phase. In fact, there's been, in the 6 years in the record that we've had that criteria, there's been 7 sudden stratospheric warmings, because in a few of the years we had 2 sudden stratospheric warmings, which is shown by the double circle. And so that compares to, you know, for example, a westerly QBO in La Nina, where the frequency is only 0.47. On the other hand, this has happened a lot more often. This combination has happened a lot more often, 15 times compared to the only 6 times that we've had an easterly QBO and La Nina. That could change this year, because it's looking like we could get the elusive La Nina easterly QBO combination perhaps this winter. So we'll have to see if that has an influence. Okay, I wanted to quickly provide some case studies to see how these are used when you're forecasting, and the difficulties that are inherent with using these events to make predictions. So this is an example from February 12th, 2018, and I showed a similar plot for this event earlier. These are just the polar cap geopotential height anomalies. This is essentially showing the northern annular mode index. So you can see that during this event, there was some pretty fast downward coupling to the surface, and there were some substantial surface impacts, including a shift to a negative AO and negative NAO. And this led to a wide variety of weather changes, including a snowstorm that the UK office named the Beast from the East. And there was snow as far south as Rome, which is fairly unusual. In addition, there were 4 nor'easters that March that sort of pummeled into the northeast region associated with the strong blocking over Greenland that was set up there. And so if we look at sort of what were the temperature effects in the 45 days after the event, The plot on the left is, again, just a composite map after all sun warming events, so sort of the average of what typically happens. And then the plot on the right is showing the weather average for the 45 days after this particular event. And so there's actually pretty decent agreement, I would say. You know, much colder temperatures over Asia, we're seeing warmer temperatures over Greenland, colder over parts of the US, but you'll notice one of the big differences here is that the US was quite a bit warmer than what we would predict from a sudden stratospheric warming. And so one of the things that's particularly important over North America is to realize that the sudden warming occurs in the context of many other influences, many with a much stronger influence over North America. So for Europe, sudden stratospheric warmings can be, you know, really dominate any other influence. But for North America, I would say that ENSO and the MJO are typically going to be really the lead contenders. And when you're making these seasonal forecasts, the sudden warming can just change that a little bit. So during this particular year, we had a really strong amplitude phase 6-7 MJO going on. And this is the surface impacts in temperature that are associated with that phase of the MJO. So you can see here much warmer conditions over the US associated with this MJO event. Additionally, there was a La Nina that year, and some climate change influence, particularly warmer temperatures over a lot of the CONUS region. And so when you add these together, this is obviously very rudimentary, with the sudden warming influence, perhaps that explains how we end up with these observed temperature anomalies over North America that don't really look that much like the sudden warming influence. But there's a lot of questions about this that I think we haven't really figured out yet. Whether these responses are linear, are they independent from each other? Which of the factors matter the most, and does that vary in time? And how much is just internal variability? So these are some big problems for using sudden stratospheric warmings as predictors, particularly over the US. I do think that they can be important, but it's just one factor in a broad spectrum of things that can be going on. The inability to forecast the sudden warming more than 15 days out, which the models really struggled to predict this event in 2018, does have a big influence on their forecast. And we can see that here for, this is the NCEP CFSV2 model, making predictions for March temperatures. And so these are different initialization dates. And so in January of 2018, you can see that this forecast model was predicting extremely warm temperatures over Europe for March. Now, around February 1st, it started to be able to predict that a sudden warming was going to happen. So about 10 days before the event actually did happen, it started to realize there would be a giant stratospheric warming event. And so you can see that forecasts actually start to change and incorporate the influence of the stratosphere downward. And so by the time we're initializing when the actual sudden stratospheric warming occurred on February 12th, you start to see these cold temperature anomalies. And these maps look a lot better compared to the observed March anomalies than earlier initializations without that stratospheric information. I will mention that if you do the same exercise for a forecast over the US, the impact on the skill was much less obvious. So again, it has a big influence over Europe, but it's a little bit harder to pick it apart over the United States. Another case study might be January 5th, 2021, which was this last year. And so this was a really nice sudden stratospheric warming that had a persistent downward influence. You can see its largest influence appears to be sort of early February. And this is at the same time that we had that really cold Texas outbreak of cold air. However, and Steve Baxter pointed this out at the last seminar, if we look at the week 3-4 Heidke skill scores over CONUS, the skill actually decreases after the event occurs in the stratosphere. So we're really not, the model is not getting any additional skill from knowing this event happened, at least for the CONUS region at week 3-4. So this is just a picture from climatereanalyzer.org showing the 2-meter temperatures that happened around February 15th, 2021. And this is when we had those really disastrous impacts on Texas energy and things like that that led to multiple deaths, 58 deaths in this region. The thing that I think it's very unknown yet exactly what the role of the stratosphere was in this event. I think it did help set up conditions for this, but there were, again, other things going on. And there's a number of studies that have not been published yet, but that I've seen that are investigating this event in particular. But one thing that I found interesting when I was watching this event unfold is that at the beginning, when the sudden warming actually happened in January, and this is shown here in this middle plot that shows the geopotential heights at 50 millibars. This is January 5th to January 15th, so right after the sudden warming happened. You can just see this average, this higher than normal heights over the Arctic cap, but it's very centered on the pole. And it wasn't until the vortex started to move around a bit and get pulled apart that we start to see this formation of the low heights over the eastern or over the central Canadian region that's been associated with that cold air outbreaks in some of those studies I referred to earlier. And so I think something similar to what those studies were showing could have been going on in this case, where it took a while. We had a regular sudden stratospheric warming that maybe had a stronger influence over Europe at first, but it wasn't until that vortex moved around a bit and got stretched out that we got the impacts over North America. And more work on that will have to be done to confirm that hypothesis. So just a few more slides left, and I just want to talk briefly about what about this coming winter in the stratosphere. And so this is a plot from the NOAA Climate Prediction Center, and the gray shading and the yellow line just give that climatology as I showed before. And overplotted on it in the red line is what's happening this year, and the little green squiggly lines are the forecast from the GFS model. And so what we can see is that it seems like a pretty typical vortex so far. There was a period where it was briefly slightly weaker than average in late October, but generally it looks pretty typical for this time of year. It's now strengthening quite a bit. The factors that might go into making a forecast of the stratosphere include the fact that there's going to be a La Nina, maybe not as large as originally predicted from what I've seen the last couple of days. There's likely going to be an easterly QBO as well. And so those two things could suggest that the chances of getting the sun's stratospheric warming are a bit higher this year. However, if we look at the S2S models and what they're forecasting, most of them are showing a positive NAO for February and March. And so depending on whether a sun warming does actually occur, you could really upend these forecasts entirely, because once that happens, it really changes what the seasonal forecast models will predict after that point. So this is how the sun warmings contribute to the uncertainty in the seasonal forecast. The last thing I wanted to talk about, because it's a frequent media question that I get, so I figured some of you might be interested in it, is whether climate change is making colder outbreaks associated with a weaker polar vortex occur more often. And the idea is that Arctic sea ice loss in particular can weaken the polar vortex, making colder outbreaks occur more often, even as the global climate is warming. So I guess there's a couple points that I'd like to make that argue against this idea. The first is that if you look at any climate change scenario, if CO2 concentrations continue to increase, winters will overwhelmingly become warmer everywhere, not colder. We don't see any increasing cold signals if we just look at the climate model simulations. The other thing is that there's no agreement across these climate models, even in the sign of the response of the strength of the stratospheric polar vortex to increase CO2, even though all of these models show substantial sea ice loss, which to me kind of makes it say, at the very least, this mechanism is not the dominant one that's happening, because the models are showing either a very strong strengthening of the vortex, some of them are showing a very strong weakening of the vortex, but there's no agreement. An equal number of models are showing both things happening. And so it's really hard to say that this theory is, that we can actually say anything about it right now. There's just too much uncertainty. I will say that there's more robust indication of changes in the shape or the location of the polar vortex in observations and in future climate change scenarios. So those things certainly could also influence weather in the future. And some of the models are more in agreement about the fact that the vortex might shift, for example, off the pole somewhat. And so those sorts of things might actually be quite relevant, and trying to understand them could be important. So to conclude, I hope I've shown you that information about the polar stratospheric vortex is useful, at a minimum, during windows of opportunity for improving predictive skill on S2S timescales. But there are inherent limitations of S2S forecast when the polar vortex event itself is only predictable at 10 to 15 day lead times. Once an event is underway, the stratosphere does offer a significant persistent source of skill for days to weeks. And there is some potential for probabilistic forecasts of these events at longer leads, but I think a lot more work remains to determine how much skill can be gained when we don't know when the actual event will happen. And I hope I've also emphasized that there's different types of polar vortex characteristics beyond a typical sun stratospheric warming that may be more useful for improving North American forecasts. Just to end, I want to share some resources. Hopefully you guys will get access to these slides, but these are some sources of stratospheric monitoring and prediction. So the Climate Prediction Center has a nice website that they're actually updating currently, and Dr. Laura Siasto is sort of the stratospheric lead at the CPC. And so you can reach out to her if you have questions about this. Zachary Lawrence runs a great independent website with different forecasts of stratospheric diagnostics, and NASA has a nice site as well using the GEOS forecast model. And then I point also to ECMWF's medium range and long range forecasting charts, because they show some really nice North Atlantic oscillation predictions in their long range forecasts, as well as 45-day polar vortex wind forecasts. And the C3S Copernicus seasonal forecasts are also very helpful for looking across models and what different models are forecasting. So thank you. This is my Twitter account if you want to follow me on Twitter, or feel free to email me with any questions. Thanks.
Thank you, Amy. And I would encourage folks, if you're on Twitter, to follow Amy for keeping up on the research and the latest that's going on here. If you have any questions, please type them into the chat and Jenna will bring them up. And in the interim, actually, Amy, I had quite a number of questions before we started, but if you didn't, you answered every single one of them, including
oh, that's good.
Including what we might expect with climate change. This is really outstanding, and I know a lot of the folks that have asked me about this topic, I think, are quite pleased with what you presented. So I'll say thank you up front.
Sure.
And then check with Jenna to see if we've had any questions put into chat.
Yep. Hi, guys. We have one question so far, but just as a reminder, I sent out the link to where these recordings are posted. And Amy, if you just share the slides with me, I can also have Jim Z, who posts them on our website, share the PowerPoint as well. Just be aware that they are made public. So, so our first question is from Victor Murphy. When a SSW event occurs, how does one know which continent the cold air will spill down into? North America, Asia, Europe, so on.
Yeah, I would say you don't necessarily know. I think it increases the odds of a cold air outbreak anywhere across the mid-latitudes. You can tell from the average composite that most often the signal's strongest over Eurasia. So that's where we expect more often to see the cold air outbreak. But that doesn't preclude it from occurring over North America either. So I think that's one of the challenges right now, is trying to understand what is it that suddenly makes this happen over the US. And sometimes it doesn't, and sometimes it does, we don't know. So I think we're still trying to understand those factors.
Okay, great. I don't see any other questions, but I'll add on to Victor's question and kind of ask you, I know you said it's challenging, but does it have to do with maybe the shape of how the event occurs? Like you were saying, how it elongates, like does it, have you seen like ways of which, where it would spill into different places based on the shape of it?
Yeah, it does seem like, and this is somewhat anecdotal, but you know, I've watched a lot of these events unfold, and what typically happens is, especially when you get a one of these split events where the sun warming breaks into two pieces, if one of those vortices then goes over North America, that's often when we get the associated changes over North America. Whereas if you get an event where the vortex just sort of displaces over Eurasia, sometimes you get stronger effects than over Europe. And so I think, I don't know if that's really been quantified that much thus far. And so this is really where the research in this is going now, is trying to understand how can we use this information better than what we're currently doing to get predictability in particular regions.
Okay, great. I still don't see any additional questions. If anyone has one, please put it in the chat box. Again, the recorded seminars, I put the link there, but it will also be, I will also include it in the follow-up email that goes out. And with that, Ray, do you have any final comments or questions?
Yeah, I might have one add-on question there, Amy. You know, you shared a lot, and it's great to see the research papers shared so folks can go dig in those. But where are we from a big picture perspective in the research process toward understanding or maximizing the forecast skill? And sudden, it seems like we're still at a pretty immature point yet.
Yeah, I would agree with that. I think that, you know, unlike something like ENSO, which has been used for a long time in seasonal forecasts, the stratosphere is really a pretty new arrival to the scene in terms of being appreciated for its potential influence on the surface at these week-long timeframes. And so I think that there's still a lot to be done, and hopefully over time we'll start to more and more understand exactly how this information can be used, because I do think it could be very helpful once we understand what processes are driving certain types of weather better.
All right. Well, thanks again very much for presenting for us today, and for folks in the field for taking time to sit in on the presentation. Hope you'll find it useful and help you answer some questions to your staffs and media folks and the public. So thanks for attending this. And if you attended the prior webinars this year, we're already looking to plan some for the upcoming time frame. So if you have ideas for next year of things you would like to see, drop me or Jenna an email, or Andrea Bear out in Western Region, and we'll see what we can work up. Well, thanks, folks, and have a good rest of the afternoon.
Oh, Ray, one last question just came in, and since we have a couple of minutes, is that okay, Amy?
Yeah.
Sure. Okay, so can increased Arctic outbreaks across the Northern Hemisphere still allow average temperatures to warm if the warm spells cover a larger area than the polar vortex areas?
So I'm not totally sure I understand, but I think what you're saying is because when you get a wavier jet stream, you also have some areas getting warmer temperatures compared to colder temperatures. And I guess what I would say is generally, you know, as proof of this, when we do an average of the surface temperatures after these events, what's really coming out is the cold and not the warm. And so I think that's reflecting the fact that you're more often getting the cold coming down and not so much the warm going up, although that does seem to occasionally happen. However, I think that one thing that can be true is that, let's say in a future where the polar vortex actually strengthens, which a number of the climate models show it doing, that could actually make the global warming changes worse in those regions as a just dynamical side effect of what the polar vortex is doing. So you can actually, depending on what the polar vortex does in the future, it could have cause a lot of uncertainty in how strong that global warming change signal will be over the mid-latitudes. So that sort of thing can be very important, I think.
Okay, great. Thanks so much, Amy. And Ray, you kind of stole my thunder a little bit earlier, but I was going to mention that we are in the process of planning the next round of seminars. Hopefully we'll start them up maybe in February of 2022 next year, give a break for the holidays, and so we can get ourselves coordinated. If anyone has suggestions for topics or speakers, please, definitely send them in to myself or Ray or Andrea, and we'll get those on the books. But we were talking with CPC earlier about doing a handful of maybe a couple, 2 or 3 seminars on their drought monitoring and forecasting products. So we'll be looking forward to those. And I guess that is all. I don't see any other questions. So I want to, well, and then lastly, I do want to thank Andrea and Ray for coordinating and facilitating all of these seminars the past, I don't know, I guess we've been doing them since earlier this summer. So I want to thank them for doing that. And I guess have a great day. And thank you so much, Amy, for ending our seminar series with a great topic and a great presentation. By the way, you did an awesome job. And have a great one.